Today we'll discuss 5 very important theorems in differential calculus which are very important for IIT JEE as well as for CMI and ISI. Now the first one is Bolzano's theorem. Now this theorem says if a continuous function has values of opposite sign inside an interval, then it has at least one root in that interval. So suppose this is our x-axis and we have 2 points A and B such that value of function at A and B are of opposite sign. Now case 1, when f is positive and fb is negative. Now since the function is continuous, when it goes from A to B, it will take all the values between A and B. So there will be at least one point in this interval AB, say C, such that fc is equal to 0. And if A is negative and B is positive, then also it will intersect x-axis at least at one point. There could be more than one point of intersection or more than one roots between A and B, but it will have at least one root in this interval. So this theorem is, if we have function fx in the interval AB such that fa into fb is less than 0 and this function f is continuous, that means at least one root of the equation fx equal to 0, it will lie in this interval AB. We are given this polynomial px, which is 2013 x to the power 2012 minus 2012 x to the power 2011 minus 16x plus 8. Then px equals 0 for x belongs to 0 to 8 to the power 1 upon 2011 has which of the following options. Now this 8 to the power 1 upon 2011, it is greater than 1. So what we'll do is, we'll find value of this function at 0. Value of this function at 0 is 8. Now we'll also find value of this function at 1. So value at 1 is 2013 minus 2012 minus 16 plus 8. So it'll be 1, 9. 9 minus 16 is minus 7. So from here we can say P0 into P1, it is less than 0. So at least one root will lie in 0, 1. Now we'll also find P 8 to the power 1 upon 2011. Now here what we'll do is, we'll take x to the power 2011 common. So it'll be 2013x minus 2012 minus 16x plus 8. Now x to the power 2011 will be simply 8. So it will be 8 into 2013x minus 8 into 2012 minus 16x and then plus 8. Now here we'll take these two together. Now if we take 8x common, it will be 2011, and here also if we take 8 common, it will be 2011. So we can write this as 8 into 2011 into x minus 1. Now since this value is greater than 1, so this value is again greater than 0. So from here we can say P1 into P 8 to the power 1 upon 2011, it is less than 0. So this equation will have at least one real root in 1, 8 to the power 1 upon 2011 using Bolzano's theorem. So this equation will have at least two real roots, and that's your option D. Now the next question is, let A, B, C be real numbers, a n equal to 0 and alpha is root of this equation. So if alpha is the root of this equation, we can write a square alpha square plus b alpha plus c equals to 0, and that's our first equation. And beta is root of the second equation. So it will be a square beta square minus b beta minus c equals to 0, and that's our second equation. Now it says if alpha is less than beta and both of them they are positive, then this equation, which is a square x square plus 2bx plus 2c equals to 0, has a root gamma that always satisfies. Now what we'll do is we'll assume a function fx which is a square x square plus 2bx plus 2c. Now since it is a polynomial function, this function is a continuous function. Now if we find f alpha will be a square alpha square plus 2b alpha plus 2c. Now b alpha plus c is minus a square alpha square. So it will be minus a square alpha square, which is less than 0. And if we find f beta, it will be a square beta square plus 2b beta plus 2c. Now b beta plus c is a square beta square. So it will be 3 times a square beta square, which is greater than 0. So from here we can say f alpha into f beta, it is less than 0. Now from Bolzano's theorem, we can say that at least one root of the equation fx equals to 0 will lie between alpha and beta, which means gamma lies between alpha and beta, and that's your option D. Now the second theorem is intermediate value theorem. It says if f is a continuous function whose domain contains the interval ab, then it takes on any given value between fa and fb at some point within the interval. Now what does that mean? Suppose again we have this x-axis and y-axis, and then we have 2 points, say a and b, and then suppose this is fa and this point is fb. Now graph of this function will start at a and then it'll take any form and finally it ends at b. Now it doesn't matter which shape it takes, but as long as this function is continuous, it will take all the values between fb and fa. So if we have any value, say fc, which lies between fa and fb, then there will be at least one point in between ab such that this function takes the value fc, and that is a intermediate value theorem. Now one important result that we generally use while solving problems is we know that fb plus fa by 2, it lies between fa and fb, and from intermediate value theorem we can say that there exists at least one point c such that fc is fb plus fa by 2, where c lies in ab. Now here the question is use intermediate value theorem to show that this equation has a solution in the interval 1 to 2. Now what we'll do is we'll take this function fx as 2x cubed plus x square minus x plus 1 in the interval 1 to 2. Now what is f1? f1 is 2 plus 1 minus 1 plus 1, it is 3. And if we find f2, f2 is 16 plus 4 minus 2 plus 1, which is 19. Now this 5, it lies between fa and fb. That means from intermediate value theorem, we can say that there exists a point c in the interval 1 to 2 such that f of x equals 5. Now here the question is prove that there exists a number x such that x to the power 200 plus 1 upon 1 plus sine square x equals 200. Now what we'll do is we'll take this as some function fx and it'll be x to the power 200 plus 1 upon 1 plus sine square x. Now if we find f0, f0 is 1, and if we find f2, f2 will be 2 to the power 200 upon 1 plus sine square 2. Now this 200, it lies between 1 and 2 to the power 200 plus 1 upon 1 plus sine square 2. So from intermediate value theorem, we can say that there exists a point C in the interval 0 to 2 such that fx equals 200. So there exists at least one root in the interval 0 to 2. Now the third important theorem is Rolle's theorem. Now in Rolle's theorem we have three conditions and then statement for Rolle's theorem. So what are the conditions for Rolle's theorem? Conditions are, if function f is continuous in closed interval AB and it is differentiable on the open interval AB and fa equals fb. So if all the three conditions are met for Rolle's theorem, then the theorem says there exists at least one c in open interval AB such that f dash c is 0. Or in other words, we can say that at least one root of the equation f dash c equals to 0 will lie in open interval AB. If a plus b plus c is 0, then the quadratic equation 3ax square plus 2bx plus c equals to 0 has which of the following condition? Now, one way of solving this question is using Rolle's theorem. Now in Rolle's theorem, we know that f dash c is 0. So that means this function, it must be a derivative of some function. If we integrate this function, we'll get ax cubed plus bx square plus cx. So what we'll do is, we'll start with the function, let fx equals ax cubed plus bx square plus cx in the interval 0 to 1. Now since it is a polynomial function, it is continuous and differentiable. Now f0 is 0, f1 is a plus b plus c, and it is given that a plus b plus c is also 0. So this function, it satisfies all the three conditions for Rolle's theorem. That means at least one root of the equation f dash x equal to 0 will lie in the interval 0, 1. Now what is f dash x? It is 3ax square plus 2bx plus c equals to 0. So at least one root of 3ax square plus 2bx plus c equals to 0 will lie in 0, 1, and that's your option A. Now here the question is, let fx be a non-constant thrice differentiable function such that fx equals f6 minus x, and it is given that f dash 0 is 0, f dash 2 is 0, and f dash 5 is also 0. Now determine minimum number of zeros of gx, which is f double dash x whole square plus f dash x into f triple dash x. Now we can write this gx as d by dx of f dash x into f double dash x. Now let us take this as some function hx. So let hx equals f dash into f double dash x. Now it is given that f dash 0 is 0, f dash 2 is 0, and f dash 5 is 0. Now we differentiate this, we'll get f dash x equals minus f dash 6 minus x. So if we put x as 0, we'll get f dash 0 equals f dash 6, and if we put x as 2, we'll get f dash 2 equals f dash 4, and if we put x as 5, we'll get f dash 5 equals f dash 1, and if we put x as 3, we'll get f dash 3, and all of them, they are 0. So this f dash x, it will have 1, 2, 3, 4, 5, 6, 7, at least 7 zeros. So this function f dash x will have at least 7 zeros. Now using Rolle's theorem, we can say that in between any two zeros of f dash x, there will be at least one zero of f double dash x. So in between 7 zeros of f dash x, there will be at least 6 zeros of f double dash x. So this function hx, it will have at least 13 roots or 13 zeros. Now since this function hx, it is continuous and differentiable, then in between at least 13 zeros, there will be at least 12 roots of h dash x equals to 0, and h dash x is nothing but gx. So the minimum number of zeros of gx will be simply 12, And that is the answer to this question. Now the theorem is Lagrange's mean value theorem or the first mean value theorem. Now it says if fx is a function which satisfies the following two conditions, and the first one is fx is continuous on the closed interval ab and it is differentiable on the open interval ab, then there exists a point c in open interval ab such that f dash c is equal to fb minus fa upon b minus a. Now what is the geometrical interpretation of that? Now simply geometrical interpretation means, suppose we have this function between a and b. Suppose this is your point a and this is your point b. This is fa and this is your fb. Now when we say fb minus fa upon b minus a, it is nothing but it is y2 minus y1 upon x2 minus x1, which is slope of this line. So it is average slope. Now Lagrange's mean value theorem says there exists point C in between AB at which instantaneous tangent is equal to this average tangent. So we have this C in between AB such that f dash C is equal to FB minus FA upon B minus A. So there are two conditions. It should be continuous in closed interval AB and differentiable in open interval AB. Then we'll always get a value C in AB such that f dash C is equal to FB minus FA upon B minus A. Now here the question is, let f be a function defined on 0 to 8 to R and it is such that f0 is 0, f4 is 1 and f8 is 1, then which of the following holds good? Now if we use Lagrange's mean value theorem on this function fx in the interval 0 to 4, we can say that there exists some point c1 in the interval 0 to 4 such that f dash c1 equals f4 minus f0 upon 4 minus 0, where c1 lies between 0 and 4. Now f dash c1, it will be f4 which is 1 and f0 is 0, so it will be 1 by 4. So there exists a point c1 in the interval 0 to 4 such that f dash c1 is 1 by 4. If it is in 0 to 4, it will also be in 0 to 8. So that means this option A, it is correct. Now if we use intermediate value theorem in the interval 0 to 4, we can say there will be some point C2 such that F4 plus F0 upon 2 equals FC2, where C2 lies in the interval 0 to 4. Now F4 is again 1, so we can write FC2, this value will be 1 by 2. Now if we multiply these two results, we can write f dash c1 into fc2 will be 1 by 8 or 8 f dash c1 into fc2 will be 1. So that means this option C is also correct. Now using the given points, it is not possible to have 12 in the denominator. So that means this option B cannot be decided from this given data. Now what about this option D? Now it says that there exists some alpha beta in the interval 0 to 2 such that this integral from 0 to 8 ft dt is equal to 3 alpha square f alpha cube plus beta square into f beta cube. Now here what we'll do is we'll assume a function gx, which is this integral from 0 to x cube ft dt. Now if we find g dash x will be fx cube into 3x square. Now what we'll do is we'll use Lagrange's mean value theorem on this function gx. First in the interval 0 to 1, we can write there exists a point g dash alpha such that g1 minus g0 upon 1 minus 0, where alpha lies in the interval 0 comma 1. And then we'll use LMVT theorem again in the interval 1 to 2, and we can write there exists a point beta in the interval 1 to 2 such that g dash beta will be equal to g2 minus g1 upon 2 minus 1. Now g dash alpha will be 3 alpha square f alpha cube and g dash beta will be 3 beta square f beta cube. So if we add them, we can write 3 alpha square f alpha cube plus 3 beta square f beta cube, and it'll be equal to G2 minus G0. Now G0 is 0, so this is equal to G2, and G2 is this integral from 0 to 8 ft dt. So from here we can say this integral from 0 to 8 ft dt will be equal to 3 alpha square f alpha cube plus 3 beta square f beta cube. So that means this option D is also correct. So correct options are A, C and D. Now here the question is, for a function fx equals x cos 1 by x when x is greater than or equal to 1, which of the following options are correct? Now first we'll find this limit, which is limit x tends to infinite f dash x. For that we need to differentiate this function. We'll find f dash x. Now f dash x will be x. Now derivative of cos is minus sine 1 by x, and then derivative of 1 by x is minus 1 upon x square plus, now derivative of x is 1 and then cos 1 by x. So we can write this function f dash x as 1 by x sine 1 by x plus cos 1 by x. Now if we take this limit x tends to infinite f dash x, now this is 0 and this is cos 0 and cos 0 is 1. So value of this limit is 1. That means this option B, it is correct. Now next we'll come to this option D, where we need to find whether f dash x is strictly decreasing in this interval. What we'll do is we'll differentiate this function again. We'll write f double dash x and it'll be 1 by x cos 1 by x minus 1 upon x square plus sine 1 by x as it is, and then minus 1 upon x square, and then minus sine 1 upon x and minus 1 upon x square. Now these two, they'll cancel. We'll write f double dash x as minus 1 upon x cube cos 1 by x. Since x is greater than or equal to 1, this is positive, and when x is greater than or equal to 1, 1 upon x is less than or equal to 1, which is less than pi by 2. So this cos is also positive, and then we have this negative sign. That means f double dash x is less than 0. And when f double dash x is less than 0, it simply means that f dash x is strictly decreasing function. So f dash x is strictly decreasing in the interval from 1 to infinite, and that's your option D. Now when we know f dash x is strictly decreasing, then for any x which is less than infinite, f dash x will be greater than f dash infinite. Now f dash infinite is this limit x tends to infinite f dash x, which is 1. So from here we can say this f dash x is strictly greater than 1. So for any x, f dash x must be greater than 1. Now for A and C, we'll use Lagrange's mean value theorem. So if we use Lagrange's mean value theorem, we can write fx plus 2 minus fx upon x plus 2 minus x, it is equal to sum f dash c. Now we know that any derivative, it is greater than 1. So it will be greater than 1. So from here we can say fx plus 2 minus fx, it must be greater than 2, and that's your option C. So the correct options are B, C and D. Now there is an alternate form for Lagrange's theorem, and which is prove that the expression fx plus h equals fx plus h f dash x plus theta h, where theta lies between 0 and 1, is an equivalent form of the mean value theorem. Now we know that mean value theorem says if function f, it is continuous in closed interval ab, and it is differentiable in open interval ab, then we'll get at least one c in between ab, such that f dash c equals fb minus fa upon b minus a. Now what we'll do is we'll take A as x and we'll take B as x plus h, where h is greater than 0. Now clearly the C, it should lie between x and x plus h. So we can write this C as some x plus theta into h, where the value of theta lies between 0 and 1. Now we substitute ABC in this equation. We can write f dash x plus theta h will be equal to fx plus h minus fx upon h. Now we rearrange it. We can write fx plus h as fx plus h into f dash x plus theta h, where theta lies between 0 and 1. So that's your alternate form for Lagrange's mean value theorem. It also says find the value of theta in terms of x and h when fx equals x cube. So now for this question, fx is equal to x cube. Now on the left hand side, it will be x plus h whole cube. This is x cube. This is h. Now f dash x is 3x square. So it will be 3 and then x plus theta h whole square. Now we can write this as x cube plus h cube plus 3x square h plus 3x h square will be x cube plus 3h x square plus theta square h square plus 2 h theta x. Now here x cube and x cube, it will cancel. 3x square h will also cancel. So we'll get h cube plus 3x h square will be equal to 3 theta square h cube plus 6h square theta x. Now we can cancel h square. So here will be h and here also will be h. So we can write this as h plus 3x and it will be 3 theta square h plus 6 theta x. Now we can write this as a quadratic in theta. So it will be h theta square plus 2x theta minus x plus h by 3 equals 0. Now we solve this quadratic equation. We'll get theta as under root of x square plus xh plus h square upon 3 minus x upon h. Now we rationalize it. We can write this as x plus h by 3 upon under root of x square plus xh plus h square by 3 plus x. Now if we take this limit h tends to 0, then we can write limit h tends to 0 theta equals, now this is x and here will be 2x. So this limit will be 1 by 2, which lies between 0 and 1. And that's your alternate form for Lagrange's mean value theorem. And finally we have our fifth theorem, which is Cauchy's mean value theorem or extended mean value theorem. Now it says if the functions f and g are both continuous on the closed interval ab and are differentiable on open interval ab, then it says there exists some c in open interval ab such that fp minus fa into g dash c, it is equal to gb minus ga into f dash c. Now if gb is unequal to ga and g dash c is unequal to 0, then we can write this as f dash c upon g dash c will be equal to fb minus fa upon gb minus ga. And that's our statement for Cauchy's mean value theorem. Now here the question is, find whether the functions fx equals x square minus 2x plus 3 and gx x cube minus 7x square plus 20x minus 5 satisfy the conditions of Cauchy's mean value theorem in the interval 1 to 4. Now conditions for Cauchy's mean value theorem is there must exist a point C in the interval 1 to 4 such that f dash c upon g dash c, it must be equal to f4 minus f1 upon g4 minus g1. Now what is f dash c? F dash c will be 2c minus 2, and g dash c, it will be 3c square minus 14c plus 20, and it will be equal to f4. What is f4? f4 is 16 plus 3, 19. 19 minus 8 is 11. 11 minus f1. f1 is 4 minus 2, so it will be 2 upon g4. g4 is 64 minus 16 into 7 plus 80 minus 5, which is 27 minus g1. g1 is 21 minus 12, which is 9. So this is 9 by 18, which is 1 by 2. So we'll get 4c minus 4, and it will be equal to 3c square minus 14c plus 20, or 3c square minus 18c plus 24 equals 0, which is c square minus 6c plus 8 equals 0. So value of c is either 2 or value of c is 4. Now this c equals to, it lies in the interval 1 to 4. So the corresponding value of c in this case is 2, and these two equations, they satisfy condition for Cauchy's mean value theorem. Now here the question is, let fx and gx be two differentiable functions such that f2 is 8, g2 is 0, f4 is 10, and g4 is 8. Then prove that g dash x equals 4 f dash x. If we write Cauchy's mean value theorem, we can write f dash x upon g dash x will be equal to f4 minus f2 upon g4 minus g2 for at least one x in the interval 2 to 4. Now we can write f dash x upon g dash x as, now what is f4? f4 is 10, and 10 minus 8 is 2, and g4 is 8, and 8 minus 0 is 8. So this is 1 by 4. So from here we can say this g dash x is equal to 4 f dash x. So there must exist at least one point x in the interval 2 to 4 such that g dash x is equal to 4 f dash x. Now here the question is, for every twice differentiable function f defined on r and minus 2 to 2 with f0 square plus f dash 0 square equals 85, which of the following statement is or are true? Now first we look at the statement C, which is limit x tends to infinite fx equals 0. Now since this function is bounded between minus 2 and plus 2, we can choose this function fx to be some sine function. Say 2 sine kx, and we can adjust this k so that f0 square plus f dash 0 square, it is equal to 85. Now if we take limit on this function, then this limit will be oscillating value between minus 2 and plus 2. So for all the functions, this limit, it won't be 1. That means option C is incorrect. Now we'll come to this option B. Now what we'll do is, we'll apply Lagrange's mean value theorem on this function fx in the interval minus 4 to 0. We can write there is at least one x naught in the interval minus 4 to 0 such that f dash x naught, it is equal to f0 minus f minus 4 upon 0 minus 4. Now we can write mod of f dash x naught, it will be mod of f0 minus f minus 4 upon 4, and it is less than or equal to mod of f naught plus mod of f minus 4 upon 4. Now maximum value of this function is 2. So this is always less than or equal to 1. So from here we can say there is at least one x naught in the interval minus 4 to 0 such that mod of f dash x naught, it is less than or equal to 1. That means this option B is correct. Now this option A is, there exists R and S such that R is less than S and f is 1, 1 in the open interval Rs. Now this statement is equivalent to proving that in some interval f dash x is unequal to 0. Because if f dash x is unequal to 0, then in the smallest interval fx is either increasing or decreasing, and therefore it will be a 1, 1 function. Now we look at this given condition, which is f0 square plus f dash 0 square equals 85, then f dash 0 square will be 85 minus f0 square. Now minimum value of f0 square is 0 and its maximum value will be 4. So from here we can say f dash 0 square, it will be less than or equal to 85 but greater than or equal to 81. So from here we can say value of f dash 0 will lie between 3n under root 85, and thus f dash 0 is unequal to 0. So if we choose a small interval in the neighborhood of 0, say from minus delta to plus delta, in this interval this function will be monotonic and thus it will be a 1, 1 function. So that means this option A is correct. Now this option D is, we need to prove that there exists some alpha in minus 4 to 4 such that f alpha plus f double dash alpha equals 0 and f dash alpha is unequal to 0. Now what we'll do is we'll assume a function hx, which is fx square plus f dash x square, and we know that value of h0 is 85 and this function is both continuous and differentiable. Now we take any point c1 in the interval minus 4 to 0, then hc1 will be f c1 square plus f dash c1 square. Now maximum value of fc1, it can be 4, and there exists a point c1 such that this f dash c1 is less than or equal to 1. So this hc1 will be less than or equal to 5. Now in the same way, we can choose a point c2 in the interval 0, 4 such that hc2 is f c2 square plus f dash c2 square, which is less than or equal to 5. Now in this interval from c1 to c2, which includes 0, we have this condition that the value of hx, it is 5 or less than 5 at c1 and c2, and then at 0 this value is 85. So this function, since it is continuous and differentiable, it will attain a maxima at some point, say alpha. So there will exist a point alpha in the interval minus 4 to 4 such that h dash alpha is 0. Now h dash alpha will be 2f alpha into f dash alpha plus 2f dash alpha into f double dash alpha equals 0. Now we take 2f dash alpha common, then f alpha plus f double dash alpha will be 0. Now if we take f dash alpha equals 0, then we'll end up getting a contradiction. So we'll discard this case. So we'll assume f dash alpha is unequal to 0. Then we'll have this condition that f alpha plus f double dash alpha, it should be 0 for some alpha lying between minus 4 to plus 4, and that's your option D. So the correct options are A, B and D. Now here the question is, let A, B, C be non-zero real numbers such that this integral from 0 to 1 is equal to this integral from 0 to 2, and we have the same function. Then we need to find location of roots of ax square plus bx plus c. Now this ax square plus bx plus c, it is within this integral. Now what we'll do is, we'll assume a function f, say ft, which is given by this integral from 0 to t, 1 plus cos x to the power 8 into ax square plus bx plus c into dx. Now both these functions, they are continuous and differentiable, and integral of continuous and differentiable function is also continuous and differentiable. So this function is continuous and differentiable. Now what is f1? f1 is this integral from 0 to 1 1 plus cos 8x ax square plus bx plus c dx. And what is f2? f2 is this integral from 0 to 2, 1 plus cos x to the power 8 ax square plus bx plus c dx. Now it is given that f1 equals f2. So this function, it again satisfies all the three conditions of Rolle's theorem. That means at least one root of the equation f dash t equals to 0 will lie in the interval 1, 2. Now what's f dash t? F dash t will be 1 plus cos t to the power 8 into at square plus bt plus c equals to 0. Now this, it cannot be 0. That means at least one root of ax square plus bx plus c equals to 0. It must lie in the interval 1 to 2, and that's your option B. Now here the question is, let f be continuous on 0, 1 such that f0 equals f1. Then prove that there exists a point c in 0, 1 by 2 such that fc equals fc plus 1 by 2. Now what we'll do is, we'll assume a function gx which is fx minus fx plus 1 by 2. Now since f is continuous, fx minus fx plus 1 by 2 will also be continuous. Now we find g0 will be f0 minus f1 by 2, and if we find g1 by 2, it will be f1 by 2 minus f1. Now it is given that f1 is equal to f0, so we can write this as f1 by 2 minus f0. So this is a minus b and this is b minus a, which simply means that g0 into g1 by 2, it is less than or equal to 0, which means there exists at least one c in the interval 0 to 1 by 2 such that gc is 0, which means fc equals fc plus 1 by 2, and that is the answer to this question. Now here the question is, f is a differentiable function and gx is a double differentiable function such that mod of fx is less than or equal to 1 and f dash x is equal to gx. If f square 0 plus g square 0 equals 9, then prove that there exists some c in the interval -3 to 3 such that gc into g double dash c is less than 0. Now we are given that g0 square plus f0 square equals 9. We can write g0 square, it is equal to 9 minus f0 square. Now minimum value of f0 square is 0 and maximum value is 1. So we can write g0 square, it will be less than 9 and greater than or equal to 8. So from here we can say mod of g0, it will lie between 2 and 3. Now what we'll do is, we'll apply Lagrange's mean value theorem for this function fx in the interval 0 to 3. We can write there exists some f dash c1 which is equal to f3 minus f0 upon 3, and we'll take this mod sign also, where c1 lies between 0 and 3. Now mod of x minus y is less than or equal to mod of x plus mod of y. Now maximum value of this function fx is 1, so it will be always less than or equal to 2 by 3, and f dash x is gx, so we can write mod of gc1, it is less than or equal to 2 by 3. Now if we apply Lagrange's mean value theorem for this same function fx in the interval -3 to 0, we can write gc2, it is equal to mod of f dash c2, and it will be equal to f0 minus f minus 3 upon 3, which is again less than or equal to mod f0 plus mod f minus 3 upon 3, which again is less than or equal to 2 by 3, where C2 it lies in the interval minus 3, 0. Now without loss of generality, we can assume that Gx is greater than 0. And if Gx is positive, then G0 it will lie between 2 root 2 and 3. Now if we look at this function Gx between minus 3 and plus 3, we have a point C2 in between 0 and minus 3 at which value is less than or equal to 2 by 3. So suppose this is the value, and we also have another point C1 in the interval 0 to 3 where the value again is less than 2 by 3. Now value at 0, it lies between 2 root 2 and 3. So this value will be greater than 2 root 2. So this Gx will start from this value 2 by 3, it will increase, and then whichever way it will decrease, finally it will go to C1. So if the function increases, so this function has to increase and decrease at some point. So there will be at least some point C in the interval C1 and C2 where this graph will be concave down. And when the graph is concave down, in that case, G dash C is less than 0. So there must exist a point C in the interval minus 3 to 3 such that GC into G double dash C is less than 0. Now here the question is, suppose f2 is 1 and f dash x is less than or equal to 5, and it should also say this function f is continuous and differentiable. We need to find lower bound for f minus 2 and upper bound for f5. Now we can write f dash x equals f2 minus f minus 2 upon 2 minus of minus 2 from Lagrange's mean value theorem. Now it says f dash x is less than or equal to 5. So we can write f2 is 1 minus f minus 2, and it will be less than or equal to 20. So we can write f minus 2 is greater than or equal to minus 19. So lower bound of f minus 2 is minus 19. And now for f5 we can write f dash x equals f5 minus f2 upon 5 minus 2, again from Lagrange's theorem, and this again is less than or equal to 5. Now f5 minus 1, it is less than or equal to 15. That means f5 is less than or equal to 16. So an upper bound of f5 is 16. Now the question is, in 0 to 1, Lagrange's mean value theorem is not applicable to which of the following functions. Now we know that for Lagrange's mean value theorem, there are two conditions. First, the function should be continuous in closed interval AB, and it should be differentiable in open interval AB. Now we'll start with this first function. Now f 1 by 2 negative, which is left hand limit at 1 by 2, it is 0. F 1 by 2 positive, which in this case is also f 1 by 2, it will be 0. So this function is continuous in 0 to 1. Now what about differentiability? We'll differentiate this function. We'll find f dash x will be minus 1 when x is less than 1 by 2, and will be 2 1 by 2 minus x into minus 1 when x is greater than or equal to 1 by 2. Now what is its left hand derivative? F dash 1 by 2 negative, it is minus 1, and f dash 1 by 2 positive, it is 0. That means this function is not differentiable at x equals 1 by 2. And since this function is not differentiable in 0 to 1, that means Lagrange's mean value theorem, it is not applicable to this function fx. Now what about sin x upon x? f0 is 1, our limit x tends to 0 positive, sin x upon x it is 1. So this function is right continuous. So this function is continuous in 0, 1. Now we know that in between 0 and 1, this function sin x upon x, it is differentiable. So this function is continuous and differentiable. So Lagrange's mean value theorem, it can be applied to it. Now what about this third function, x into mod x? X into mod x is x square when x is greater than 0. And it is minus x square when x is less than 0. So this function again is continuous and differentiable. Now what about mod x? Now between 0 and 1, this function is continuous and differentiable. So the only function where Lagrange's mean value theorem is not applicable is this option A. Now here the question is, let fx and gx be differentiable functions such that f dash x into gx is not equal to fx into g dash x for any real x. Now show that between any two real solutions of fx equals to 0, there is at least one real solution of gx equals 0. Now what we'll do is, we'll prove this question using contradiction. So what we'll say is, let us assume between two roots of fx equals to 0, say alpha and beta, there is no real root of gx. Now we'll assume a function hx which is fx by gx in between alpha and beta. Now since both the functions, they are continuous and differentiable, gx is unequal to 0 and h alpha is 0 and h beta is also 0. That means this function hx, it satisfies all the conditions for Rolle's theorem. Now Rolle's theorem says there exists at least one x in the interval alpha comma beta such that h dash x is 0. Now what is h dash x? It is gx into f dash x minus fx into g dash x, and it will be equal to 0. So from here we get this condition that gx into f dash x, it is equal to fx into g dash x. But in the question it says f dash x into gx is not equal to fx into g dash x. So there is a contradiction. So from contradiction we can say that in between two roots of fx, there must be at least one real root of gx equals 0. Now here the question is, for every pair of continuous functions f and g such that maximum of fx equals maximum of gx, the correct statements are. Now let us say this maximum value is m and f1 takes this maximum value at c1 and gx takes this value at c2. That means fc1 equals gc2 and it is equal to m, and this m is greater than or equal to all fx's and gx's. Now what we'll do is we'll define a function hx which is fx minus gx. Now if we find hc1 will be fc1 minus gc1. Now fc1 is m, so this value is always greater than or equal to 0. And if we find hc2 will be fc2 minus gc2, and now gc2 is maximum value, this is always less than or equal to 0. So from here we can say hc1 into hc2 is less than or equal to 0. Thus from Bolzano's theorem we can say there exists a point C in the interval c1 and c2 which lies in the interval 0 to 1 such that hc is 0, which means such that fc minus gc is 0. So there must exist a point in the interval 0 to 1 where fc is equal to gc. Now if we look at these options, we can write this A as f square c minus g square c plus 3 fc minus gc equals 0, which is fc minus gc into FC plus GC plus 3 equals 0. And since it is 0, that means this statement A, it is correct. And if we look at not C but D, then it is FC square minus GC square will be FC minus GC into FC plus GC. Now again FC minus GC is 0. So that means this statement D is also correct. So the correct statements are A and D. Now in this question it is given that F0 equals F1. Now if F0 equals F1 and the function is continuous and differentiable, then from Rolle's theorem we can say that there exists a point C in the interval 0, 1 such that f dash C is equal to 0. So we have a point in 0, 1 where f dash C is 0. Now we'll use Lagrange's mean value theorem in the interval C to X. Then we can say there exists a point D such that f double dash D, it is equal to f dash X minus f dash C upon X minus C. Now we'll take absolute value of this expression. Now it is given that f double dash X, it is less than equal to 1. So it is less than or equal to 1 and f dash C is 0. So from here we can write mod of f dash X, it is less than or equal to X minus C. Now since X and C, they lie between 0 and 1, that means X minus C is always less than 1. So from here we can say mod of f dash X, it is less than 1. And that is what we need to prove. And here the question is, if a function is defined from R to R and it is a differentiable function such that f dash X is greater than 2 times fx for all x belongs to R and f0 is 1, then which of the following options is correct? Now what we'll do is, we'll write this as f dash X minus 2 fx and L be greater than 0. Now we multiply it with e to the power minus 2x. We can write e to the power minus 2x into f dash X minus 2 e to the power minus 2x into fx, it is greater than 0, or d by dx of e to the power minus 2x into fx, it is greater than 0. And if we choose a function gx, which is e to the power minus 2x into fx, we can say that this gx, it is an increasing function. Now if we choose x greater than 0, we can write gx will be greater than g0. Now gx is e to the power minus 2x into fx and will be greater than g0, which is e to the power 0, 1 and f0 is also 1. So from here we can say this fx will be greater than e to the power 2x. That means option A is correct. Now in the question we are given that f dash x, it is greater than 2fx and 2fx is greater than e to the power 2x. So it will be greater than e to the power 2x, which is greater than 0. So from here we can say f dash x is greater than 0. Therefore fx is an increasing function. So fx is increasing in 0 to infinite. So correct options are A and C. Now here the question is, if fx is a twice differentiable function such that fa is 0, fb is 2, fc is minus 1, fd is 2 and fe is 0, where a is less than b, is less than c, is less than d, is less than e, then minimum number of zeros of gx, which is f dash x square plus f double dash x into fx in the interval a to e is. Now we can write this gx as d by dx of f dash x into fx. So if we take this as some function hx, which is f dash x fx, first we will find minimum number of roots of hx in this interval. Now what you're given is 5 points a, b, c, d and e. Now value at a is 0, value at b is 2, value at c is minus 1, value at d is 2 and value at e is 0. Now from Bolzano's theorem, we can say that there will be at least one root between B and C, and there will be at least one root between C and D. So there will be 1, 2, 3 and 4. Between A and B, there will be at least 4 roots of fx. And in between any two root, using Rolle's theorem, there will be at least one root of f dash x. So it will have at least 3 roots of f dash x. So this hx, it will have at least 7 root. Now using Rolle's theorem, we can say that in between any two roots, there will be at least one root of h dash x, which is this function gx. So this gx will have at least 6 roots. So the minimum number of zeros of gx will be 6, and that is the answer to this question. Now here the question is, if b is greater than a, then we need to find location of roots of this quadratic equation x minus a into x minus b minus 1 equals 0. Now we know that coefficient of x square is positive. That means this is quadratic expression opening upwards. So the roots are alpha and beta. Now if we write this as some function fx, which is x minus a, x minus b minus 1. Now what is the value at a? fa is minus 1 and fb is also minus 1. Now since both at a and b, this function takes a negative value, that means this point a, it must lie here, and b, it should lie here. That means this alpha, it should be less than a, and beta, it should be greater than b. So answer should be one root in minus infinite to a and the other in b to infinite, and that's your option D. Now here the question is, if it is given that a is greater than b, it is greater than c, it is greater than d, then prove that this quadratic equation x minus a, x minus c plus 2, x minus b, x minus d equals to 0 will have two real and distinct roots. Now what we'll do is, we'll assume a function fx, which is x minus a into x minus c plus 2 x minus b into x minus d. Now since it is a polynomial function, it is continuous function. Now if we find fa, now a minus a is 0, so it will be 2 a minus b and a minus d. Now since a is greater than b and a is greater than d, fa is greater than 0. And if we find fb, fb will be b minus a into b minus c. Now b minus a is negative and b plus c is positive, so it will be less than 0. So here we are getting this condition that fa into fb is less than 0. Then from Bolzano's theorem, we can say that at least one root of fx equal to 0 will lie in the interval ab. Then the same way we'll find fc. fc will be 2 times c minus b into c minus d. Now c minus b is negative and c minus d is positive, so it will be less than 0. And fd is d minus a into d minus c. Both of them, they are negative, that means fd is greater than 0. So from here we get this condition that fc into fd, it is less than 0. So again from Bolzano's theorem, we can say that at least one root will lie in the interval CD. Now since it is a quadratic equation, it cannot have more than 2 roots. That means exactly one root will lie between a and b, and exactly one root will lie in c comma d. Now here the question is, let f be a continuous function defined from 0 to 1 to 0 to 1, whose range is from 0 to 1. Then show that there exists a c in 0, 1 such that fc is equal to 1 minus c. Now what we'll do is, we'll assume a function gx, which is fx minus 1 plus x. Now since f is a continuous function, this function gx is also continuous. Now if we find g0 will be f0 minus 1, and since range of this function is from 0 to 1, this value will be less than or equal to 0. And in the same way, we can find g1, and g1 will be f1 minus 1 plus 1, which is f1, and since its range is from 0 to 1, it is greater than or equal to 0. So from here we can say g0 into g1, it is less than or equal to 0. Now from Bolzano's theorem, we can say there exists a point C in 0, 1 such that GC is 0. Now if we put GC as 0, we can write FC minus 1 plus C equals to 0, or FC equals 1 minus C. Now here the question is, if fx and gx are differentiable functions such that f0 is 5, g0 is 0, f2 is 8 and g2 is 1, show that there exists a number C in the interval 0 to 2 satisfying f dash C equals 3 g dash C. Now we can solve this question using Rolle's theorem, and we can solve this question using Cauchy's mean value theorem also. So if we use Rolle's theorem, we'll define a function hx, which is fx minus 3 gx. Now this function is continuous and differentiable. Now if we find h0 will be f0 minus 3 g0. Now f0 is 5 and g0 is 0, so h0 is 5, and h2 will be f2 minus 3 g2. Now f2 is 8 and g2 is 1, so 8 minus 3 is 5. So we are getting this condition that h0 equals h2. Then from Rolle's theorem we can say there exists at least one C in the interval 0 to 2 such that h dash C is 0. Now h dash C is f dash C minus 3 g dash C equals 0, which is f dash C is equal to 3 times g dash C. Now if we solve the same question using Cauchy's mean value theorem, we can write f dash C upon g dash C will be equal to f2 minus f0 upon g2 minus g0 for C lying in the interval 0 to 2. So we'll write f dash C upon g dash C will be equal to f2 minus f0. Now f2 minus f0, it will be 8 minus 5, 3 upon g2 minus g0, which is 1. So from here we can say f dash C is equal to 3 times g dash C, and which is what we need to prove. Now here the question is, if function f be continuous and differentiable, then we need to show that f4 minus f2, f4 square plus f2 square plus f2 into f4 by 3, it is equal to 2f square C into f dash C. Now this is a minus b into a square plus b square plus ab. So we can actually write this as f4 cube minus f2 cube upon 3, and it should be equal to 2 times f square C into f dash C. Now what we'll do is we'll assume a function gx, which is fx cube. Now since f is continuous and differentiable, gx is also continuous and differentiable function. That means Lagrange's mean value theorem can be applied to this. So there exists a point C in the interval 2 to 4 such that g dash C is equal to g4 minus g2 upon 4 minus 2. Now what is g dash x? G dash x is 3 fc square into f dash C, and here it will be f4 cube minus f2 cube upon 2. Now we can rearrange it. Now if we rearrange it, we can write this as 2 fc square into f dash C will be equal to f4 cube minus f2 cube whole divided by 3. And this is what we need to prove. Now here the question is, let a be greater than 0 and f be continuous in minus a to a. Suppose that f dash x exists and f dash x is less than 1 for all x lying between minus a and plus a. If f is a and f minus a is minus a, show that f0 it is equal to 0. Now if we use Lagrange's mean value theorem in the interval minus a to 0, we can say there exists a point C1 in the interval minus a to 0, which is equal to f0 minus f minus a upon a. Now f dash x, it is less than or equal to 1. So we can write f0 and f of minus a is minus a. So it will be f plus a and is less than or equal to a. So from here we can say f0, it must be less than or equal to 0. Now if we use Lagrange's mean value theorem in the interval 0 to a, we can say f dash c2 is equal to fa minus f0 upon a, and it again is less than or equal to 1. Now fa is a, so we can write a minus f0 less than equal to a, which means f0 is greater than or equal to 0. Now here we are getting the condition that fx is less than equal to 0, and here the condition is fx is greater than or equal to 0. So from here the only condition that we'll get is f0, it must be equal to 0, and this is what we need to prove. Now here the question is, let a, b, c be three real numbers such that a is less than b, it is less than c, and fx is continuous in ab and differentiable in ac. Also f dash x is strictly increasing in ac. Then we need to prove this result. Now if we use Lagrange's mean value theorem for this function in the interval a to b, we'll get some c1 such that f dash c1 equals fb minus fa upon b minus a, where c1 lies between a and b. And if we use Lagrange's mean value theorem in the interval b to c, we can write f dash c2 such that fc minus fb upon c minus b, where c2 is in the interval b and c. Now we know that c1 is less than c2 and f dash x is strictly increasing. It means f dash c1 will be less than f dash c2. So from here we can write fb minus fa upon b minus a, it must be less than fc minus fb upon c minus b. Now we cross multiply, we can write c minus b fb minus c minus b fa will be less than b minus a fc minus b minus a fb. Now we take fb on left hand side and fa on right hand side, we can write c minus a fb will be less than b minus a fc plus c minus b fa, which is what we need to prove. Now here the question is, prove that if f is differentiable on ab and if fa equals fb equals 0, then for any real alpha there exists an x in ab such that alpha fx plus f dash x is 0. Now what we'll do is we'll assume a function gx, which is e to the power alpha x into fx. Now this gx, it is continuous and differentiable, and if we find ga is 0 and gp is also 0. So that means this function gx, it satisfies all the three conditions for Rolle's theorem. There must exist a point x in the interval a comma b such that g dash x is 0. Now what is g dash x? It is e to the power alpha x into f dash x plus fx into e to the power alpha x into alpha, it is equal to 0. Now e to the power alpha x, it cannot be 0. So from here we'll get this condition that there must exist an x in the interval a to b such that f dash x plus alpha fx, it must be 0. Now the question is, let f be continuous on AB and differentiable on AB such that fa equals a and fb equals b show that there exists distinct c1 and c2 in AB such that f dash c1 plus f dash c2 equals 2. Now what we'll do is, since the function is continuous and differentiable, we'll apply Lagrange's mean value theorem to this function fx in the interval a to a plus b by 2 and also in the interval a plus b by 2 to b. Now we apply Lagrange's mean value theorem. In first interval, we'll say there exists at least one c1 such that f dash c1 equals f a minus b by 2 minus fa upon b minus a by 2, where c1 lies in the interval a comma a plus b by 2, and the same way we can write there exists a point c2 such that fb minus f a plus b by 2 upon b minus a by 2, where c2 lies in the interval a plus b by 2 comma b. Now we add them, we can write f dash c1 plus f dash c2, it will be equal to b minus a by 2, and here f a plus b by 2 will cancel, so we'll get this as fb minus fa. Now it is given that fb is b and fa is a, so it is 2 times b minus a upon b minus a. Now this b minus a will cancel, so we'll get 2 distinct points c1 and c2 such that f dash c1 plus f dash c2, it is equal to 2. Now here the question is, using Lagrange's mean value theorem or otherwise prove that difference of square root of 2 consecutive natural numbers greater than n square is less than 1 by 2n. So we have 2 numbers, say n and n plus 1, which are greater than n square, and we need to prove that under root of n plus 1 minus under root of n, it is. Now what we'll do is we'll assume a function fx which is under root x in the interval n to n plus 1, and we'll apply Lagrange's mean value theorem. So we'll get at least one c in the interval n to n plus 1 such that f dash c is under root of n plus 1 minus under root n upon n plus 1 minus n, which is under root of n plus 1 minus under root of n. Now what is f dash c? F dash c is 1 upon 2 root c. Now c lies in n and n plus 1, therefore c is also greater than n square, or 1 upon c is less than 1 upon n square. So from here we can write 1 upon under root c will be less than 1 by n. Using this result we can say under root of n plus 1 minus under root of n, it is less than 1 by 2n, and this is what we need to prove. Now here the question is, let f be a function defined on r to 0, 1 be a continuous function, then which of the following functions have or has the value 0 at some point in the interval 0, 1. Now if we look at the function in this option A, e to the power x minus this integral from 0 to x ft sin t dt. Now we know that when x belongs to 0, 1, e to the power x will lie between 1 and e, and ft sin t, it will lie between 0 and 1. As the value of this function lies between 0 and 1, and value of sin x also lies between 0 and 1, and thus this integral 0 to x ft sin t dt, this value will also lie between 0 and 1. Now clearly e to the power x will be greater than integral from 0 to x ft sin t dt, and therefore this gx is always greater than 0, and thus it cannot be 0. So this option A is incorrect. Now what about function in this b? So for b, let us take gx as x to the power 9 minus fx. Now what is g0? G0 is minus f0, which is less than 0, and g1 is 1 minus f1, and maximum value of f is less than 1. So this is greater than 0. So from here we can say g0 into g1 is less than 0, and thus from Bolzano's theorem we can say there exists a point c in the interval 0, 1 where gc is 0. So that means this function will have a value 0 at some point in the interval. Now for this third case, when gx is fx plus this integral from 0 to pi by 2 ft sin t dt. Now this fx is positive and this ft sin t is also positive. This gx is always greater than 0, and thus it cannot be equal to 0. So C is incorrect. Now what about this option D? Now for this option D, we'll take gx as x minus this integral from 0 to pi by 2 minus x ft cos t dt. Now again, if we find g0, g0 is minus this integral from 0 to pi by 2 ft cos t dt, and g1 will be 1 minus this integral from 0 to pi by 2 minus 1 ft cos t dt. Now this value is less than 1, and therefore g1 is greater than 0. So again from here we can say g0 into g1, it is less than 0, and from Bolzano's theorem again we can say that there is at least one root in 0, 1. So that means option D is also correct. So the correct options are B and D. Now here the question is, let fx equals 4x cubed minus 3x squared plus 2x plus 1 and use Rolle's theorem to prove that there exists a c in 0 to 1 such that fc is 0. Now what we'll do is, we'll assume a function gx which is x to the power 4 minus x cubed minus x squared plus x. Now this function is continuous and differentiable, and if we find g0, g0 is 0 and g1 is also 0. So this function gx, it satisfies all the three conditions of Rolle's theorem. That means there must exist a c in the interval 0 to 1 such that g dash c is 0. Now derivative of gx is fx. So that means there must exist a point c in 0 to 1 such that fc is 0. Now here the question is, let fx equals x to the power alpha log x when x is greater than 0 and 0 when x is equal to 0. Rolle's theorem is applicable on f if alpha is which of the following. Now we know that conditions for Rolle's theorem are function should be continuous differentiable and fa must be equal to fb. Now x to the power log x will be continuous and differentiable in open interval 0 to 1, and also f0 is 0, and if we put x is 1, log 1 is 0. So we have no problem with this condition and differentiability. We just have to check its continuity. Now this function should be right continuous at 0. So Rolle's theorem will be applicable to this function if f0 positive will be equal to f0 which is 0. That means this limit x tends to 0 positive x to the power alpha log x, it must be 0. Now if alpha is less than 0, then in that case it will be of the form log x upon x to the power minus alpha. Now log 0 is minus. Now here the question is, let f be a twice differentiable function such that f double dash x is greater than 0, f1 by 2 is equal to 1 by 2 and f1 equals 1. Then which of the following is correct? Now what we'll do is, we'll assume a function gx which is fx minus x. Now this function is continuous and differentiable, and if we find g1 by 2, g1 by 2 will be 0 and g1 will also be 0. So this function gx, it satisfies the condition for Rolle's theorem. That means there exists a point c in the interval 1 by 2 to 1 such that g dash c is 0. It means f dash c minus 1 equals 0, that is value of f dash c is 1. Now c is less than 1 and it is given that f double dash x is greater than 0. That means f dash x is an increasing function. So we can write f dash c will be less than f dash 1. Now f dash c is 1. So from here we can say f dash 1 is always greater than 1, and that's your option D. Limit is 0. So in this case, f0 positive will be equal to f0. So Rolle's theorem is applicable for this function if and only if alpha is greater than 0. That means the only correct option in this case is this option D. Now here we are given fx and gx, and we are given values at -1, 0 and 2. And it says in each of the intervals -1, 0 and 0 and 2, the function f minus 3g double dash never vanishes. Now we need to find which of the following statement is true. Now if we consider a function hx, which is fx minus 3gx, and if we consider Rolle's theorem in the interval -1 to 0, this function is continuous and differentiable. What is h minus 1? H minus 1 is f minus 1 minus 3 g minus 1, which is 3 minus 0, which is 3. And what is h0? H0 is f0 minus 3 g0. Now f0 is 6 and g0 is 1, so it will be 6 minus 3, 3. So that means we are getting this condition that h minus 1 equals h0, which simply means that from Rolle's theorem we can say that at least one root of the equation h dash x equals to 0, which is f dash x minus 3 g dash x equal to 0, will lie in the interval -1, 0. Now since this second derivative never vanishes, there will be only one root. So we can say exactly one root will lie in -1, 0. In the same way, if we use Rolle's theorem for fx minus 3gx in the interval 0 to 2, we know that h0 is 3. Now what is h2? H2 is f2. F2 is 0 and minus 3, which is plus 3. So again h0 equals h2. So again from Rolle's theorem we can say there will be at least one point in 0, 2 such that f dash x minus 3 g dash x equals 0. And here also there will be this exact condition, not at least. So the correct options are options B and C. Now here the question is, if fx is continuous and differentiable in -3 and 9 and f dash x lies between -2 and 8, where x lies between 3 and 9, and let n be number of divisors of the greatest possible value of f9 minus f minus 3, then find sum of digits of n. Now using Lagrange's mean value theorem we can write there exists a point C in the interval -3 to 9 such that f dash c is f9 minus f minus 3 upon 9 minus 3, which is 12. Now it is given that value of f dash x lies between -2 and 8. So we'll get this maximum value when the value of this derivative is 8. So maximum value of f9 minus f minus 3, it will be 12 into 8, which is 96. Now this is 2 to the power 5 into 3. Now we need to find number of divisors. Now number of divisors is given by 5 plus 1 plus 1 plus 1, which is 12. And if we find sum of digits in this case is simply 3. So answer to this question is 3. Now here the question is, let f be a continuous function on 0 to 1, differentiable in 0 to 1 such that f1 is 0, then there exists some c such that which of the following option is correct. So what we'll do is we'll define a function gx which is x into fx. Now this function is continuous, it is differentiable, and if we write g0 is 0 and g1 is also 0 since f1 is 0. So this function, it satisfies all the three conditions of Rolle's theorem. Then using Rolle's theorem statement, we can say there must exist at least one c in the interval 0, 1 such that g dash c is 0. Now g dash c is c into f dash c plus fc equals 0, which is your option D. Now the question is, if y equals fx is a twice differentiable function such that fa equals fb equals 0 and this function fx is positive, then which of the following is correct? Now using Rolle's theorem, we can say there is at least one point in the interval AB such that f dash c is 0. So this function, it will have a critical point in this interval AB. Now since value at A is 0 and value at B is 0 and at some point C it attains a maximum value. Now since it starts from 0 and it ends with 0, so there will be at least one point in the interval AB where it has a local maximum. If it has a local maximum at C, that means its second derivative, it must be less than 0. So f double dash c, it must be less than 0 for some c belongs to AB, which is your option A. Now the question is, if f double dash be continuous on AB and differentiable on AB, then prove that fb minus fa minus b minus a by 2 f dash a plus f dash b equals minus b by a whole cube by 12 into f triple dash d for some real d lying between a and b. So what we'll do is, we'll assume a function gx which is fx minus fa minus x minus a by 2 into f dash x plus f dash a plus a into x minus a whole cube. Now if we put x as a, we'll get ga equals 0 and we'll choose this value a such that gb is also 0. Now if we put x as b, we'll get fb minus fa minus 1 by 2 b minus a f dash b plus f dash a plus a into b minus a whole cube, and it'll be equal to 0, which is similar to expression that we need to prove. Now we need to find value of this a. Now since this function is continuous and differentiable and g equals gb, so there exists a point c in the interval ab such that g dash c is 0. If we differentiate this function, we can write this function as 1 by 2 f dash c minus f dash a minus 1 by 2 c minus a f double dash c plus 3a c minus a whole square equals 0. And this is our, say, second equation, and this is our first equation. Now what we'll do is, we'll define a function h in the interval AC such that hx is 1 by 2 f dash x minus f dash a minus 1 by 2 x minus a f double dash x plus 3a into x minus a whole square, which is similar to this expression except that this is hc. Now this function is again continuous and differentiable. Now ha is again 0 and hc is equal to g dash c, and it will also be 0. So again from Rolle's theorem we can say there exists at least one d in the interval a to c such that h dash d is 0. Now if we differentiate this function, we can write h dash x as 1 by 2 f double dash x minus 1 by 2 x minus a f triple dash x minus 1 by 2 f double dash x plus 6a into x minus a. Now this f double dash x will cancel. Now Rolle's theorem says there will be at least one point D where this derivative is 0. So we can write minus 1 by 2 d minus a f triple dash d plus 6a d minus a will be 0. We'll get the value of a as 1 by 12 f triple dash d. Now if we put the value of a in this first equation, we can write fb minus fa minus 1 by 2 b minus a f dash b plus f dash a, and if we take this expression on the right hand side, we can write this as minus 1 by 12 b minus a whole cube into f triple dash d, and this is what we need to prove in the question.